Finally, we are at reaction number 5. Reaction number 5 was another Friedel craft, and it's Friedel craft alkylation. Okay, well, we just talked about acylation, and acylation added a carbon onto the benzene, and alkylation is in reference to the R group, the infamous R group of organic. So it's just basically adding on an R group, just an alkyl chain, and the answer is yeah. That's it. That's all you got to do. So we'll come back and we'll look at benzene. So here's benzene. Snooty little old benzene. I don't want anything to do with anybody. I'm just in my own little world until we give it an RCl for our 5th reaction. Well, the RCl, do you remember what catalyst we had to use for the acylation? That was a Friedel craft. This is a Friedel craft. No difference in the catalyst. We slap on an AlCl3. Now, we don't need water. And the reason is because with the acylation, remember we added the C double bond O on. And the AlCl3 love to hang out with that oxygen. Positive, negative, opposites attract. Well, here we don't really have a oxygen. And because of that, we don't need water. So this is really the only catalyst that we have to write on the arrow for the Friedel craft alkylation. AlCl3, that's it. No water needed because there's nothing that water needs to prevent to happen. I'm not going to get that side product. I'm not going to get the byproduct. So in this reaction template, I'm going to take my benzene, which is right there. That benzene has a hydrogen on it, just like all the other benzenes. And then we off of the molecule. And then we add on, what do we add on? Well, remember chlorine? Chlorine's still ugly. No makeup is ever going to make chlorine pretty. Sorry. So that chlorine is a very good leaving group. That's going to be pulled away from the aluminum chloride, just like it did before. The aluminum is in a 3-way relationship with all of these chlorines and suck all the money away. And that aluminum is going to be positive, and that chlorine is going to be negative because it's electronegative, and we get an attraction. So chlorine says, see ya, carbon, and then boom, off it goes. And what we have left over is a R group that is positive. And there's my electrophile piece. That electrophile piece gets added on to the benzene, and there we go. Simple as that. But there's a trick. Oh, no. Whenever you say a trick, that means something tricky's coming. Well, yeah, that's called a trick. That's just the way it is. What I need you to keep in mind, and a lot of people forget this, so it's not really a trick, it's just forgetfulness. This is forming an R group is really just a carbon, right? It's something carbon, blah, 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 blah. So this is a carbocation that is forming here. What do we know about carbocations? Chemistry 251, Orgo 1 told us everything we needed to know about carbocations. Carbocations have a stability. Tertiary, secondary, primary. Those were our 3 major ones. Told you organic was foundational. The foundation's coming back. Is your foundation cracked? Because if so, you might need to go back and review carbocations. So this carbon, which is positively charged, is a carbocation by definition. Tertiary, secondary, primary is the order of ranking of stability. And that means, as in those reactions with Orgo 1, that rearrangement can take place if it can. Folks, this is no exception. There's no exception here at all. Rearrangement can take place if the possibility exists. So let me give you an example. Here we're going to take benzene, And we're going to react this with CH3, CH2, 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 Cl. And I'm going to put this with AlCl3. Now, sometimes people will write a temperature on here. Sometimes the temperature is important. If you do see a temperature on this sucker, it's typically going to be 0 degrees. So this is going to be pretty cold. Your refrigerator stays at 4 degrees Celsius. So this, very cold. We keep it on ice. As the reaction goes forward, it's a little bit better for it. So if I told you at this point, what's the product? You're going to look at this and say, oh, I know, this is pretty easy. I'm going to take my benzene, so here we go, and there's the hydrogen that comes off of that benzene, and I'm going to get rid of it. And what goes on, this chlorine leaves, and here is the R group. So CH2, 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 CH3. All right, so CH2, 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 and CH3. There we go. And then you would turn that in and you would say, here's the product. Now give me my A. And then I'm going to go, I'll give you an F, because that is not the major product. It is a product, but this is the minor product instead. Well, why? Why is that a minor product? But that's because rearrangement takes place here. Well, wait a minute. You didn't really talk about rearrangement when you talked about Friedel-Crafts acylation. No, I did not. And the reason is because that carbon was a double bonded O. That was not just a regular run-of-the-mill carbon. This carbocation, when it forms, is not going to rearrange. That is not the traditional carbocation that we have always seen in all of these reactions. That is why we didn't have to worry about rearrangement with acylation in the Friedel-Crafts category. That's not a traditional type of carbon. That is double bonded O. So that we regard a different way. But here, this is a traditional type of carbon. So when the chlorine leaves, look at what we have left. CH3, CH2, CH2, CH2. So when the chlorine leaves and whoop, off it goes, it leaves behind a positive charge. That's our electrophile. That gets added onto the benzene ring. It does get added onto the benzene ring, but that carbocation can rearrange. That is a traditional carbon that we've always seen inorganic almost every single time that we had to deal with these reactions. So right now, this is a primary carbocation. It's only attached to one other carbon. If it goes over left-handed one time, this is a secondary spot. And folks, that's exactly what happens. So the carbocation will shift over, and it will go here. But it's got to trade places with something, right? You just can't move a charge around and just forget about everything else. It's going to switch places with a nasty old disposable hydrogen that nobody wants. So this is a 1,2 hydride shift. That is something that we talked about in Orgo 1. It happened with most of our double bond reactions or triple bond reactions. Every time that we were doing reactions back in the day, we always looked for carbocation rearrangement. And here is where it's going to come into the picture again. So what this means is that this is a minor product, and it's a minor product because this carbocation, when it forms, bloop, goes one over, and that's going to be the new site of attachment. So, on my benzene ring, there goes the hydrogen, and where this carbocation is at, that is the site of attachment right there. So that carbon has a methyl group off of one side, so there's CH3, and then on the other side, a CH2, CH3. And folks, there you go. That is the major product for this reaction, and that's where it's going to get you. If you do these reactions and you forget about these carbocation shifts, this is exactly what will happen on your answer sheets. You're going to give me these answers that are super, super close, and it's going to hurt me so bad to give you an X and take off points. But deep down inside, I want you to know that I'm laughing. I got them -2. Don't let me take points off. Don't let me take the -2s off because you forgot to do the rearrangement on the product. Simple as that. That's what you always have to look for with Friedel Craft alkylation. All right, so let's do another example because that was a 1,2 hydride shift. Do you remember what the other kind of shift was? I hope so because we're getting ready to do one of them. All right, so we're going to take benzene, and this time we're going to do CH3 and carbon, and then here's a CH3, and there's a CH3, and here's a CH2, and then a chlorine. All right, and we want to know what happens. What's the major product from this? Of course, I have to add AlCl3 for this to work. So what's the major product? Okay. Well, I'll take my benzene. There we are. And then there's the bond. There goes away the hydrogen. And here's my chlorine. So I'll circle that and go, that leaves. It's ugly. Nobody wants it. And then what we have here is a carbon. I'm just going to simplify this down. I'm just going to write a carbon, and then a carbon, and then a carbon, and then a carbon here, and a carbon there. And this is where the carbocation forms, right? That's the carbon, this red one. That's the one that was attached to the chlorine. The chlorine's now gone. So that means this is the carbon that received the carbocation. It's missing the chlorine bond. Well, I need to pause, take a break, look at it, and say, does it rearrange? Okay, well, right now, this carbocation is primary. If it could move left-handed, well, this would end up being a tertiary because I have to switch spots with something, right? And right now, this carbon, the only thing that it can switch spots with is probably another carbon. So if I shove the carbocation left-handed to get that a tertiary, that carbon is going to have to shove the carbon back and switch places with it and say, okay, this is the only way it's going to work. I have to make room for you. So I've got to kick somebody out, and then you can come in and give me the carbocation. Well, if it does that, look at what happens, folks. We get a carbon, carbon, carbon. This carbocation went inward. So it goes here. That carbon still has another one on it. And it had to switch places with something. So it's going to shove that carbon down to that end. And this is the site of attachment. So that carbon is going to be attached right there. And then that carbon has a methyl group, right? There's a C to the left. And then there's another carbon that points down. So I'll do it there. And then it gives another carbon, carbon. So another 2 carbons get added on. So I've just drawn it a different way. I've just cleaned it up a little bit. That was it. But a carbocation rearrangement happens again. And because it switched places with a CH3 that was right there, this is called the 1,2 methyl shift. Again, a very common shift in Orgo 1. We saw it happen all the time in those example problems. It was part of learning the reactions and the mechanisms. And whenever these carbocations form this way, this is exactly what goes on, folks. All right? Okay, so how can I relate this to something? Well, let's take a look at this. This is a vitamin called KH2. All right, so this vitamin is basically produced in your body or used in your body. And what you see here is a phosphorylated group. If you take a look at the structure, heavily organic. Look at this. Carbon, 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 almost all the way down, right? And then here we see a double bond. So this makes this thing an alkene. But it's got these phosphate groups on it. These are oxygens. They're all negative, heavily electronegative, and it's going to take these electrons and bloop, off it goes, and it makes a very good leaving group. And look at what we've done. This forms a positive alkyl group. This is an alkyl group. I know there's a double bond in there, but it is an alkyl group all the way down. It's mainly carbon-hydrogen based. And if we bring in this type of benzene molecule, right? I mean, I see benzene in that. There's stuff on it, but there's benzene in that. Well, that benzene reaction is going to go forward, and this is the electrophile, and this electrophile gets added on to the benzene ring, and you actually see that big, long piece get attached to the benzene ring. We go through and we clean it up. Our bodies clean it up a little bit. But folks, this is basically what prevents blood clots, right? I mean, we don't want blood clots in our arteries and stuff. I mean, that leads to heart attacks and things. So because of that, we have to have a safety account to make sure that this stuff kind of handles the way it needs to be handled. And this molecule helps prevent blood clots in your body, and this molecule is made or synthesized based on alkylating a benzene ring. Now, it's not just benzene. There's other groups on it, and that's perfectly fine. We haven't made it to that point yet, but this is real life organic. And if it wasn't for this organic reaction, then folks, I hate to tell you, but you could just fall over one day, right? We're all reliant on these reactions that take place in our body. Now, here's going to be a problem. When we start looking at these types of reactions, notice what happened here. Carbocation rearranged. All right. So if I take benzene and I do a CH3, CH2, CH2Cl with aluminum chloride, and I Friedel craft alkylate it, then I'm going to end up with this benzene ring, and then off goes the hydrogen, and chlorine goes away. There's my carbocation that's formed, but it's going to shove inward. So here's the carbon, because it goes to secondary with a 1,2 hydride shift, and I have a methyl group there and a methyl group there. I don't really get a straight chain on there, do I? And honestly, no matter what I do, it will always shift. So if I wanted a 4-carbon straight chain, it would never happen. It would always shift back. If I wanted a 5-carbon, 6-carbon, 7-carbon straight chain, no straight chains. Am I going to be able to get out of this thing? And the reason is because the shifts will always happen with these. So there's got to be a way. There has to be a way that I can prevent the carbocation from forming, or from moving, not from forming. We want it to form, but we do not want it to move. So there's got to be some options for me. How do I get a straight chain onto the benzene ring and prevent that carbocation from moving and shifting? Because maybe I do want just 1, 2, 3 on that ring. So what are my options? How do we do this? Well, this leads into a special category of this particular type of reaction. And we're going to go back and look at acylation paired with reduction. Oh, gosh. What does that even mean? Well, keep in mind what we want to do. All right? So I'm going to clear the screen. But this says acylation, not alkylation. I know. That's what I meant. Let's take benzene, and let's say that I want to add on a 3-carbon chain. Well, we can do that quite easily with an acyl group. There's 3 carbons, right? There's 3 carbons. Okay, now what? Well, if I react this with AlCl3 and H2O, you would tell me, okay, well, here's my benzene ring. There's the hydrogen. Off it goes. And then this chlorine, it goes away. And this forms my carbon that's positive. But this doesn't rearrange. There's the carbon, double bond O, carbon, carbon. Look at that. Look how close I am. Look how close I am to getting that 3-carbon straight chain. If I could just get rid of that measly double bond O, then I would have it. How can I do that? Well, remember what I called this reaction? Acylation. There's the acyl part. Reduction. So inorganic reduction basically means reducing the number of C to O bonds. So that's why we call this a reduction reaction, because we're getting ready to reduce the number of C to O bonds. How do we do it? Well, with our good old Batman utility belt, an old reaction of H2 and palladium or platinum, depending on what you want to use. That's all that's required. So back in the day, we used this to break a double bond. It was a carbon-carbon double bond, but we used it to break a double bond. And guess what, folks? It also breaks the carbon double bond O as well. So this is one of the tricks that we have up our sleeve to get straight chain alkyl groups onto a benzene ring. This is how we do it. So instead of alkylating, because that's always going to give us rearrangement in products. It's always going to get rearrangement, right? If it can happen, it's going to happen. Straight chains, I'll never be able to get them on. This is the backdoor approach to getting those straight alkyl groups onto my benzene ring. You acylate it first, just like before. That gives you a carbon double bond O. And maybe you want to stop here. Maybe this is your product that you're after with the acylation reaction. If so, that's great. If not, then there is an additional reaction, a reduction part, that will reduce the number of C to double bond O's, C to O bonds, and that will completely destroy the carbonyl. And that gives us a straight chain alkyl group that goes on to that system. Now, that's only one option. Okay, I'm going to throw out another option here. The other option is a benzene ring, and let's say that we already have acylated it. All right, so let's say that this is what we have. If we want to destroy that carbon double bond O, there's another way that we could do it. We don't have to use just hydrogen and palladium or platinum. We also have another option that is H2, H2 with a little bit of base, with a little bit of heat. This is a special name, and this name is called Wolff-Kishner. And the product here is the exact same that our previous one would have given us with the H2 platinum. This H2NNH2, this has a special term. It's called hydrazine. And that's really all I'm going to say about this right now. We're going to have a lecture module that will focus on nitrogen-containing compounds. And you're going to see Wolff-Kishner come back during that reaction series or that lecture series. So I'm just kind of giving you a hint. Wolff-Kishner. Wolff-Kishner's out there. It's a nitrogen-based reaction. And that hydrazine will react with the carbonyl, destroy the carbonyl just like H2 and platinum would, and it gives you the same darn product that H2 and platinum would. So an option that we can use, that we can write down as a way to answer some of these questions that might be thrown our way. Now, one more. Wolff-Kishner was kind of new to us, right? I'm not going to classify that as a separate reaction because that really is just destroying the carbonyl bond. It had nothing to do with the benzene reaction at all. So that's not a new reaction. We're still just looking at 5 reactions here with the benzene. But there's one that we've already talked about, and that was in the last lecture module. And that was when we began talking about coupling reactions. Do you remember couples? You remember those coupling reactions with those metals that completely flip the carbons around? Go back and take a look at some of those examples. What you're going to see is that we were doing examples like this. Chlorobenzene. And then we threw in things like CH3, CH2, CH2, with maybe a boron and an OR and an OR. You remember that? Palladium, hydroxide. That was called the Suzuki. Suzuki! Okay, well, in this reaction, do you remember what happened? I told you, here's the halogens. That halogen is there. That halogen is a very good leaving group. It just so happens to be on a benzene, but that doesn't matter. We know how to get the halogen on a benzene. We know that we can add FeCl3 to get chlorine and Cl2 to get chlorine onto the benzene ring. And once we get that chlorinated benzene, then we can throw in a Suzuki reaction. Let's not forget about these. They're available. They're options to us now. And what we would end up with as a product would be the chloro getting replaced with the thing that's attached to the B, which is a CH2, CH2, CH3. Folks, look at this. This is another straight chain alkyl group that can be added onto a benzene that will prevent rearrangement from taking place. It is another utility that I can use in my Batman belt to make these reactions happen the way that I want them. But this was not the only one. Go back and take a look at those metals. Here, let's do bromo instead of chlorine, just to prove a point. And instead of Suzuki with the boron, what was another one of those? Oh, CH3, CH2, CH2, in parentheses with a 2, and a CuLi. Do you remember what that was called? That was a Gilman. What did we do during that time? We said, oh, things like aerols will work with these reactions. Okay, well, that's great news because this is an aerol compound. Bromo goes away. And what gets replaced? What gets substituted? It was what was in this parenthesis batch, right? CH2, CH2, CH3. Another way that we can get a straight chain onto a benzene ring. Organometallics. Which is why we talk about organometallics before we talk about benzene reactions. That makes sense, right? So in the next video, what I would like for you to do at this point is to answer this question. Example. For A and B, there are 2 ways to make these. How would you make them? Do both options. So, route number 1 makes that product. Route number 2 makes that product. Route 1 makes the product. Route 2 makes the product. Can you come up with 2 different ways to make molecule A and molecule B based on everything that you know so far? And the difference here, of course, is for A, not really straight chains. B, it has to be a straight chain. It has to. Look at that. No branching at all. So this one will be a little bit trickier than part A will. So that's where I'll stop this video. And then when you push play on the next one, we'll answer this question and we'll test to see how well that you did. Not too many videos left. Not too much lecture material left in this module. This next video might be the only one. Oh, what a relief. You're almost at the end.